Welcome to this lecture on the Lineweaver-Burk plot, a fundamental concept in biochemistry and zoology. Have you ever tried to measure something that keeps increasing but never quite reaches its maximum? It can be incredibly frustrating. Today, we're going to learn a brilliant mathematical trick that biochemists use to solve this exact problem. By the end of this video, you will understand how to transform complex, curved enzyme data into a simple, predictable straight line, making it easy to unlock the secrets of how enzymes work. Now that we know what we are aiming for, let us start with an intuitive analogy. Imagine you are trying to measure the absolute top speed of a race car on a track that gets increasingly difficult to drive on. As the car goes faster, it struggles more and more to accelerate. It gets closer and closer to its top speed, but never quite seems to reach it perfectly during your test. If you plot this on a graph, you get a curve that flattens out, making it incredibly frustrating to guess where that exact top speed actually lies. But what if you could use a mathematical trick to magically straighten that curved track into a perfect, predictable straight line? A straight line is much easier to read and analyze. In biochemistry, this is exactly what we do for enzymes. Building on that race car analogy, let us look at the formal definition of this mathematical trick. The Lineweaver-Burk plot is formally known as a double reciprocal plot of enzyme kinetics. Normally, when we study enzymes, we plot the reaction velocity against the substrate concentration, which produces a curved graph called a hyperbola. Instead of using those normal values, this method takes the mathematical reciprocal of both of them. By plotting 1 divided by the velocity against 1 divided by the substrate concentration, the curve is mathematically transformed into a straight line. This brilliant algebraic manipulation turns a difficult visual problem into a simple, solvable geometric one, allowing us to apply the standard equation of a straight line to complex biological reactions. You might be wondering why we need to go through the trouble of flipping our data upside down just to get a straight line. The primary reason is that the original curve approaches its maximum velocity asymptotically. This means the curve gets closer and closer to the maximum value, but theoretically never touches it, making it impossible to read the exact maximum speed directly off the graph. By converting the data into a Lineweaver-Burk plot, the straight line crosses the axes at exact readable points that correspond directly to our crucial enzyme values. Furthermore, this straight line plot is the absolute best tool biochemists have for diagnosing how different drugs and poisons inhibit enzymes. By seeing how the line shifts, scientists can instantly tell how a drug is attacking the enzyme. Now that we understand why this straight line is so useful, let us look at the mathematical formula that creates it. This is the Lineweaver-Burk equation. It perfectly matches the classic straight line formula, y equals mx plus c, that you likely learned in algebra. In this equation, v0 represents the initial velocity of the enzyme-catalyzed reaction. Vmax stands for the maximum possible velocity when all enzyme molecules are completely saturated. The bracketed S represents the concentration of the substrate we are feeding to the enzyme. Finally, Km is the Michaelis constant, which tells us the substrate concentration required to reach exactly half of the maximum velocity. Notice that our y-axis variable is 1 over v0. And our x-axis variable is 1 over s. If the maximum velocity is very high, the y-intercept becomes very close to 0. Before we move on to how this formula was derived, let us see this with a concrete example. A biochemist conducts an experiment on a new digestive enzyme and observes that the straight line crosses the vertical y-axis at a value of 0.05 minutes per micromole. We need to calculate the maximum velocity. To solve this, we simply remember that the y-intercept is mathematically equal to the reciprocal of the maximum velocity. We set 1 divided by Vmax equal to 0.05. By taking the reciprocal of both sides, we divide 1 by 0.05. This gives us a final maximum velocity of 20 micromoles per minute. Physically, this means if we gave the enzyme an infinite amount of substrate, it would process exactly 20 micromoles every single minute. Following up on that maximum velocity calculation, let us find the other crucial enzyme property. The biochemist notes that the same line crosses the horizontal x-axis at a value of negative 0.2 per millimolar. We need to calculate the Michaelis constant. We know the x-intercept is mathematically equal to the negative reciprocal of the Michaelis constant. We set negative 1 divided by km equal to negative 0.2. The negative signs on both sides immediately cancel each other out, leaving us with 1 divided by km equals 0.2. By taking the reciprocal, we divide 1 by 0.2, giving us a Michaelis constant of 5 millimolars. This tells us that a substrate concentration of 5 millimolars is required to reach half of the enzyme's maximum speed. Now that we have used the intercepts, let us look at a scenario where we use the slope instead. Imagine a student is analyzing an enzyme and finds that the plot has a y-intercept of 0.1 seconds per millimole and a slope of 3.0 seconds. We need to determine the maximum velocity first. Just like in the previous example, we begin by taking the reciprocal of the y-intercept. We divide 1 by 0.1. This simple division gives us a maximum velocity of 10 millimoles per second. This value represents the absolute fastest rate the enzyme can achieve under perfect conditions when fully saturated with substrate. With the maximum velocity in hand, we can now use the given slope to find the Michaelis constant. We write out the definition of the slope for this plot, which is the Michaelis constant divided by the maximum velocity. We set this fraction equal to the given slope value of 3.0. Next, we substitute the maximum velocity of 10 that we just calculated into the denominator. This leaves us with a simple algebraic equation. By multiplying both sides by 10 to isolate the variable, we find that the Michaelis constant equals 30 millimolar. This high value indicates that the enzyme has a rather low affinity for its substrate, requiring a large concentration to reach half its maximum speed. So we have successfully used the Lineweaver-Burk formula to find enzyme constants. This brings us to an important question. Where does this straight line formula actually come from? We must start with the foundational Michaelis-Menten equation, which describes the frustrating curved graph we are trying to fix. The initial velocity equals the maximum velocity times substrate concentration, all divided by the Michaelis constant plus substrate concentration. To fix the curve, our first mathematical step is to take the reciprocal of both sides of this equation. We simply flip the fractions upside down. This puts 1 over the initial velocity on the left and moves the addition into the numerator on the right. This setup is the crucial first step in our transformation. Continuing from our flipped equation, let us complete the derivation. We have a single fraction on the right side with 2 terms added in the numerator. We can separate this into 2 distinct fractions with the same denominator. The first term becomes Km over Vmax times S. The second term becomes S over Vmax times S. Notice that in the second term, we have the substrate concentration in both the numerator and the denominator. We can cancel these out completely. This leaves us with our final result, the Lineweaver-Burk equation. By separating the terms, we have beautifully isolated our variables to perfectly match the classic straight line equation, proving exactly why this algebraic manipulation works. Now that we have proven the math behind the transformation, let us look at the actual diagram it produces. What you are seeing here is the Lineweaver-Burk plot in its full geometric glory. Notice the vertical axis is labeled 1 over V0, and the horizontal axis is 1 over S. The straight diagonal line cuts clearly across both axes. Look at the solid dot where the line crosses the vertical axis. This is the y-intercept, which instantly reveals 1 over the maximum velocity. Now look to the left at the open circle on the horizontal axis. This is the x-intercept, showing -1 over the Michaelis constant. Finally, the steepness of the line is defined by the slope, km over Vmax. This single straight line gives us every piece of kinetic data we need at a glance. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that the Lineweaver-Burk plot is a powerful mathematical tool that transforms frustrating asymptotic curves into clean, readable straight lines using a double reciprocal method. Second, the geometry of this line is everything. The y-intercept instantly gives you the maximum velocity, while the x-intercept provides the Michaelis constant. Finally, mastering this plot is absolutely essential because it is the best visual tool we have for understanding enzyme behavior and diagnosing how different drugs inhibit metabolic processes. You now have a complete understanding of how to decode enzyme kinetics.